All right, let's start. So, welcome and thanks for being here. In the last talk, we've learned that software is eating the world and that we are the guys who are helping to make that happen, no matter if people like that or not, but we're the guys and the girls. I'm working in an office with virtually no girls around, unfortunately, and so my language is a little bit corrupted, so please apologize for that. I try to enhance that while I'm speaking here, so it's a lot better here, but anyway. So, and what I'm trying to give you is a few ideas to become even better with that. So my name is Uwe Friedrichsen, and I'm around the IT world for about 30 years, a little bit more than 30 years meanwhile, having done mostly everything you can do in the IT world, the good things and the bad things, and especially the ugly things, but today I'm not going to talk about the ugly things, but about the nicer things, so promise that. And I happen to work for Codecentric, which some of you might know. Anyway, quite cool company anyway. So, what I'm going to give you in this next 40 minutes, that's basically the baseline. So, we learned about Agile. And Agile taught us that we should focus on delivering business value, which is really important. And we learned about clean code a lot, which taught us to think about writing understandable, maintainable code and writing tests and all that stuff, which is also very important. But all of this doesn't help a bit if our application is not running reliably in production. And that's what that sentence means. We are not coding for development, we're not coding for QA, we're coding for production. It's all about production and production only. Production, first of all, means if your system isn't running smoothly, it's not making any money. It's worthless. And the customer is not satisfied, which is even worse than not making money for a few minutes, because he will probably go to a competitor and, yeah, you've lost him, probably for good. And this means your system needs to be available all the time. And availability in production means your system needs to be resilient. Resilient means that you figure out errors, problems easily, unexpected situations, and that you are able to handle that before the customer will figure out, or anybody outside the system. And the basis for that is fault tolerance. So fault-tolerant software design is about building resilient systems. Actually, there's a little bit more about resilient systems than just fault-tolerant software design, but it's quite the heart of it. And that's what I'm going to talk about a little bit in the next few minutes. And I thought about how to set up this talk and how to structure it. And I tried a few variants before, and they work quite well, but I think that setup is a little bit easier and better, and therefore I switch it a little bit. So what I'm going to do is I give you 3 case studies, how not to do things, describing them a little bit. And for every case study, I show you a few patterns, a few selected patterns, how to deal with that, how to do it better, down to the code level. So I first explain the pattern, and then I go down to the code level. So actually, it's not code that you can directly copy into your production system, so you have to polish it a little bit, fine-tune, extend it a little bit, but it's a head start. It's what you can start with. If you put that in your production code, you're probably 80% done, and then the polished thing, okay, that's the complicated stuff as usual, but a few bits and pieces are missing. Well, let's start with the first case study. Probably many of you have seen that situation before. The web server is down, no response for the customers. He's just sitting there and waiting. It's not responding. And chaos is going along, and these managers are running around screaming at everybody, and so why is the web server down? Why is our website not working? And yeah, you're doing analysis and hectical analysis. We have to figure that out and get this guy with the tie out of the room quickly. And then you figure out all your threads are waiting for the application server. And then you, okay, let's go down to the application servers and analysis now. And you figure out all your threads are waiting for the database server. And then you go down to the database server and you figure out that some guy ran a quite stupid batch job which took all the resources available and virtually the database didn't respond anymore for anybody else. So everybody's waiting for this database. Okay, now you know what to do. You kill that job and everything's fine. But in the first place, it's not a nice thing that your website wasn't responding anymore. I mean, we could do better, don't we? I mean, at least the website should have said something like, oops, we've got some internal problems at the moment, so come back later. Not just this waiting sign and waiting and nothing. Or even better, so maybe you have some caches around and you can do something like a graceful degradation of service, which means that, for instance, you could still read data from your caches, but you're not able to place any orders or any modifying actions at the moment. So you can still deliver 80% of your service, maybe, something like that. And it's a lot better. So how can we implement this? Well, lots of things you can do about that. But I've picked 3 patterns which can help to get your system better, more responsive, more resilient. Let's start with the first one, timeouts. Timeouts is basically the basis for all of that. I mean, timeouts means that you're able to get back control in the first place. I mean, in your web servers, every thread was waiting for the application server. You don't have any control anymore. You can't do anything anymore. So you need something to get back control, to give a proper answer to your customer, to give him that, oops, we've got an error page at least, or something like that. Okay, how does it work? How do we implement that? And timeouts are quite straightforward. So if we have a blocking action, we don't wait internally. We just give it a timeout. We say, we wait for 5 seconds, for 10 seconds, for whatever. But at least there's a point in time where we say, we're not going to wait any longer. It's like you're standing in the queue and nothing's going to move. Eventually we'll go away. You will not stay there forever. I mean, if it's becoming night, it doesn't help. Okay, let's implement that. Surprisingly, it's quite easy in many places in the Java standard library. There are a lot of places where you have 2 alternative options to implement your code. One alternative is that you do a blocking call, and the other one is that you do a call with a timeout. So like the wait or the thread join, something like that. There are always many methods in your Java standard library offer 2 alternatives. And even though it's many people feel uncomfortable with the second one, you should use that one. I mean, to get one thing straight, why are so many developers are not using the non-blocking variant or the variant with a timeout, but the ever-blocking one? It's quite straightforward if you think about that for a while, because we have no clue what to do if the timeout happens. And that's actually a design flaw. That's not a mistake of ourselves. I mean, we have to discuss about that. And we have to design that and think about that situation. What are we going to do if this resource we are just going to access is not going to respond? This has to be done. In a traditional setup, you have to ask an architect or designer or a requirements engineer or somebody like that. I mean, the requirements engineers just try to get away and say, oh, don't bother with the technical shit, but he has to answer you that question. I mean, it's part of his job to tell you what to do then, or at least the architect has to tell you and give you an idea how to handle that situation, how to deal with that, and stuff like that. And if you're in an agile setup, yeah, it's up to you as a team, basically. You can talk to your product owner, try to get an idea what's the best response that you can give to the customer, and he probably has an idea about that. So he said, it must never happen. And after getting away from that, after the 10 minutes of discussion or something like that, and he eventually will give in that it can happen, and then you can discuss with him how to handle that situation. So therefore, use these timeouts. And sometimes you don't have this call available in your library, so you only have that blocking call. How to handle that? It's also quite straightforward. So if you use the standard Java library, so I say here I've got an action, here's my blocking action, and what I'm going to do is I wrap that into a callable. For those who are not familiar with a callable, it's like a runnable with return values. It's quite nice abstraction, actually. So it's something you can put on a thread and it's executed, and it gives you a return value and also exceptions back, which is quite nice. And what you're doing is just something like you start a single thread executor service, one line of code, you submit your action, what you get back is a future. A future is something that you can ask for, is my action already completed? Did it complete already? And there's also a non-blocking variant, so a timeout variant which you can use, which comes back then, so sorry, not yet completed, and you can loop for that. And yeah. And then you wait for this action to complete with the timeout again. And here's the place where you put your code, what you're going to do if the timeout happens, if the resource not going to respond in time. Quite straightforward. 3 lines of code, and you can wrap every single action which is blocking with the timeout. And if 3 lines of code, I mean, we're lazy, and this makes us good, because laziness is the root of all invention, actually. And therefore, 3 lines of code is sometimes a little bit bugging to put that much code into it. So we can even have it simpler if we use something like the Guava library, for instance. So Guava library actually gives you something like the simple time limiter, which in its core does basically the same as I showed you on the slide before, but we just have 1 line of code left over. And every single call that blocked before, you can run now with a timeout. Straightforward stuff, quite easy to handle. All right, these were timeouts. Now about the polishing stuff, how to get this stuff a little bit better. So a few questions left. Also, how long should the timeout be? I mean, we are sitting here in front of our terminals and say, what do I give it? 5 seconds, 10 seconds? Whatever, no clue actually how long to wait. And okay, the first thing is quite obvious, we make it configurable, which is perfectly reasonable, because if your administrator can configure it, he knows a lot more about how this service behaves in production, how this resource access behaves, and he can probably fine-tune it quite a sophisticated way. And if we go one step further, we can even make that a little bit better by self-tuning stuff. So if you have a good monitoring, you get so standard distributions, how long these calls take usually, so the median and the percentile. So in 99% of the time, it completes, say, in something like 7.5 seconds or something like that. And then you can adopt it automatically to your percentile that you choose, which you're going to accept. Only thing, you have to put in a hard upper limit. I mean, if your resource is not going to respond anymore, your average is going to shift to eternity, and you don't want to wait eternally just because you have a self-adapting system here. So, and there are always some questions about, you said something about using explicit threads, and we are living in a Java EE world, and we've got these stupid containers, and we've heard before you must not use or you must not start explicit threads in a Java EE environment, which was true for a long time. I just read through this Java and through the servlet 3 point whatever, to the current specification, and meanwhile there's no word anymore in it that you must not start any explicit threads in it. You just must be aware about what you're doing in there, because you're stealing some threads from the container which it thinks it has control about. So if you're running on the limits of the threads that your container can control, so and quite close to the system limits, you must know that you're stealing threads. If you're a lot below the system limits, it's usually okay, but be careful, you can screw up a virtual machine, of course. And if you're still so unlucky to work still with enterprise Java beans, I'm feeling sorry about that then, but anyway, some of us are not that lucky that we can always choose what we use. There are different options to implement that stuff. There are timers and schedulers and stuff like that around. You can use quite a lot of that stuff. You will figure that out. It's quite straightforward. But in most places, what I showed you, it's perfectly fine. Okay, we've got the timeouts in place. Let's become a little bit better than just using timeouts. Let's go for the circuit breaker. I mean, your resource not available and you've got these timeouts. You figure out, it's not going to respond. And it's not going to respond over and over and over again because it's really down at the moment. And actually it's not that nice that every single request is going there to, you're going to call your resource to run into that timeout waiting for 10 seconds or whatever. I mean, we can be smarter than that. We can eventually figure out, the resource is down at the moment and let's not wait till the timeout. Just go back immediately and say, sorry, resource not available at the moment. I mean, that's a basic pattern of fault-tolerant software design. If you're going to fail, fail fast. The faster, the better. So if you're going to fail and you know that you're going to fail, don't even try to access the resource, come back immediately. And that's exactly what the circuit breaker pattern is going to implement. So the core idea is, between the client and the resource, you've got that circuit breaker. And if you do a request, it keeps track of the availability of the resource. And if the resource is available, it sends the request through. And if it's not available, it just comes back immediately and tells you, sorry, the resource is not available at the moment. So you're not going to wait for 10 seconds or longer in your code. You're immediately able to respond to your customer, I can't fulfill this request at the moment, which is a great thing. I mean, if we are going to wait for 10 seconds on our website or for 0.5 seconds, it's a big difference. And it's going to implement that with a nice little life cycle. There are a lot of implementations around in the outside. If you go to Google for the circuit breaker, I take the original one that Michael Nygaard presented in his book, Release It, which is a great book, by the way. I could recommend that to read that to everybody. It's a lot about those things. And the core idea of this state machine that it implements is quite straightforward. So every circuit breaker starts in a closed mode. So circuit breaker is closed. And then if you get a call, you pass it through, straightforward. And if the call fails, you increase a counter, so failure counter. If the call succeeds, you reset that to 0. And if you reach a threshold with your failure counter, you trip the breaker, which brings you into the next state, into the open state. Here the difference is, if you get a call, you immediately return with a failure message. Resource not available. But for not staying open eternally, you have that timeout when you look back to the resource. Is it available again? So can I close my circuit breaker again? And that's done with the third state, the half-open state. When we switch to the half-open state and we get a request, we pass it through and we observe it. If it's okay, we go back to the closed state. And if it fails, resource not yet available again, so we go back to the open state. Quite straightforward. How can we implement that? Also quite straightforward. So simple implementation here. That's just some initialization stuff, so not that interesting. Only thing maybe worth mentioning, what I'm doing here is I'm wrapping that resource call with a circuit breaker. So the assumption here is that I put a proxy around the resource calls and use that as a circuit breaker. You can implement that with decorations or whatever, so it's up to you. Here I was lazy, I just used the wrapper version. And here's the real resource access, so this access method. At the moment, in the beginning, its state is not open, so we can skip that part and go down here. We try to do the real access, quite straightforward. If the access, and should use a timeout, of course. If you have a timeout here, you fail, otherwise you succeed. I mean, the implementation of fail and succeed is also quite straightforward. So if you succeed, I was lazy here, I combined that with a reset method, I reset my counter. And if it fails, yeah, I increase my counter, and if the counter exceeds a certain threshold, I call trip breaker, which is not going to do anything else than switching the state to open and keeping track of the time when it opened, when it tripped the breaker. Yeah. And now we can come back to this method. Now we're open. And again, I was a little bit lazy to save lines of code here for presentation purposes. I first check the timeout, and then I throw that exception, so you can do that a little bit more cleanly and anything. So one call is always wasted in that implementation. And if I check the timeout, yeah, if it's bigger than that, I'm going to half open, and here another compromise that I just set the counter to threshold. So when I do the next call, it either succeeds and the counter goes back to 0 and the state is closed again, or I increase the counter again, and which is then larger than threshold again, and I switch it back to open. That's basically it. So it's just a few lines of code to implement the circuit breaker. It's surprisingly easy, actually, and it's got a big effect on the resilience of your system, how stable it is, how robust it reacts. So a few more things how we can improve that. So yeah, quite often you run in a multi-threaded environment, so you must make it you must make it ready to run in a multi-threaded environment. So make it ready for concurrency, which is actually not so much extra code to implement. It's quite straightforward. I left it out here, but you probably will figure it out. And you might check for different failure types. So sometimes you run in a timeout, but you can also have some other situations which are failure situations, like you get an immediate response, but there's nothing in it, or whatever. So different failure types you can differentiate in here. And you can also tuning the numbers of defects and the timeouts and all that stuff, which you can make configurable again or self-adjusting, as I described before. And the nice thing about that one is there are a lot of implementations out there. For instance, there's a very nice one in the Hystrix library that Netflix released, but there are also other ones. And they're already thread safe and everything's in there, so ready to use. Great stuff. Google is your friend here. You figure that out. And just a last little pattern for the sake of completeness here. It's that fail fast pattern. This pattern you're going to use is also a refinement of this stuff if you're going to access a lot of different resources in the first place. And what you're going to do here is, you know already, if you're going to fail, you should fail fast. And if you already know that one of the resources is not available, you're not starting your expensive action, which is going to access a lot of resources, like a checkout action on your shopping cart or whatever. There are a lot of expensive actions. So what you have in here, as I said, you have a request that's going to an expensive action which is going to access a lot of resources, and you don't want to execute that action if any of these resources are not available. So you have that fail fast guard in between where you get this request, it checks the resources, and if the resource is available, it forwards to the expensive action and it executes. In the other case, it just sends back the message, sorry, at the moment we cannot execute that action. And with the stuff we already have in place, it's extremely simple to implement that. So we just implement that fail fast guard. It just uses the circuit breakers and checks if all circuit breakers that I get are in the state closed, and if not all of the circuit breakers are closed, we throw that exception. And the only thing we still have to do here is then we have to put that fail fast guard in the beginning of our expensive action and provide it with all the required resources we need to access. Again, implemented in 2 minutes. And it's a lot of resilience you can build into your systems and a lot of nicer behavior. So these were the 3 patterns I want to talk about for this one. There's a lot more of stuff around, definitely. So fault-tolerant software design is a huge domain. But as I said in the beginning, I want to give you a little bit of a head start, a few ideas how to build better systems. And I want to spark your curiosity to learn more about that for sure. It's a very interesting domain. But here are some things that, again, that help you to make your systems a lot better than without it. So the next case study talked enough about the situation with the non-responding server. Here you have a little bit different behavior. So let's assume that your favorite artist, your favorite band is coming to a concert close your hometown. And this band was not there for the last 5 years, and you must go there. You definitely have to go there. I mean, you're waiting for eternity to get tickets for that band. And yeah, you're sitting there, you know when the ticket sale is going to start, you're sitting in front of your machine, you have a hot cup of coffee, you're waiting for the minutes to tick down, and then in exactly the second, you click to access the website and nothing. You're waiting. You're waiting. And as usual, if you're waiting, you're just pressing on retry, reload, reload, reload. And yeah, eventually you get into the site. But you've got the feeling that the bits are carried around by hand to your web browser. And it takes eternally until some information gets in. And you try to click through that, and this website is a catastrophe. The response times are a catastrophe. It's often nothing is going to work, and in some places, in some situations, it takes eternity to build up, and finally you get to the checkout. But unfortunately, the system insists that you only have 10 minutes for getting your ticket and checking it out, and otherwise your order will be released for other people, so you cannot keep track of tickets. So many of the sites in Germany are built that way. I'm not sure about how it's here. And just before you get through to the checkout, your session's gone. And on the Twitter stream, you read, meanwhile, that the concert is sold out. Okay, the first reaction is you want to kill somebody. You're not sure yet whom to kill, but you definitely want to kill someone. And you're definitely right, because you should kill the guy who bought this website, because you can do better. How to do that better? So there are a lot of patterns around there. I will present you one which I really like a lot. It's a so-called shed load pattern. The idea of that pattern is you've got your site, your server, and just too many requests hitting it. So you've got this overload situation. How you're going to handle that? What you're going to do here is you put a gatekeeper in front. So on the one hand, you have those clients coming in with all those requests. On the other hand, you have something in place which you should have in place anyway, no matter if you are going to implement that pattern or not, which is a monitor, which monitors several parts of the server, but especially also the load. And once in a while, the gatekeeper requests that load data, how much load is on the server. And if it's too much load, it just goes and filter out parts of the request to make sure that the server keeps responsive for the request it lets through. Okay, how can we implement this idea? First thing, I picked a quite easy one for the beginning, and we can refine that later on. So the initial idea, so let's assume we are using servlets, at least some kind of servlet container, so we can implement that as a filter. Here's just some initialization code, so let's not bother about that one. Let's go to the real do filter method of the, this request when it's coming in. And what it's going to do is, first of all, it's going to get the load. I will talk a little bit about that later, how to get that stuff. And then decide, should I shed? We'll see that on the second slide then. And if we should shed, we just come back with a 503 service unavailable with a little recommendation when to come back. So it's part of the HTTP standard, straightforward stuff. Okay, Servlet API recommends to put all that stuff into an error page which is configurable in your web XML and stuff like that, but let's just fine-tuning and polishing the stuff. The core idea is this one. And if everything's fine, yeah, we're going to move on to the next filter. Yeah, nice. And the should shed, you can implement a lot of stuff in there. I just put in a very simple example implementation, which isn't perfect, but for a start, it's a lot better than having it not in place. So I just figure out, am I still below a certain load threshold? If yes, yeah, everything's fine. So no, you shouldn't shed. And between your load and your max load, I just calculate a number between 0 and 1, and I just use a random number and figure out if that's below that number, and then yes, I should shed. So as higher as the load goes, closer as the load gets to the maximum threshold available, the higher the probability that a request is shedded. That's basically the whole magic here. I mean, about refinements in a minute. One thing which isn't so nice about that one is that we still hit the machine under load because we go to the servlet filter, so we still go on the website. It still is a lot better than executing expensive actions inside your servlet container, but still all requests hit your website. So what's even better, again, it's a lot of improvement here. What's even better is to build a proxy server, which is real gatekeeper before your website. So that all these requests that you shed are not going to hit the website first, even if it's shedded in the filter. So, but today that's not a problem anymore. So just sketched here was building your proxy servers and 20 lines of code. There was a website somewhere out there with a Node.js, straightforward stuff. Or use Vertex, for instance. It's just this much code, easily written, lots of examples around, and you can put that in there. Straightforward stuff, no magic. I mean, 5 years ago it was a little bit more of an effort to write a proxy server, but today it's virtually nothing. And sometimes it's even okay that you just have a static limit in here, something like so many requests, and then you can go with, for instance, just a limiter module which is available for Nginx or something, or some other kind of server which you can put on front of your web server to use that one. It's perfectly fine sometimes. Let's shed load. So how to improve that? So shedding strategy, yeah, you can think about a ton of variants. So more aggressively shedding in the case that your server gets under load instead, not just linear. Or in the other situations, we had ongoing sessions. So we are going to let the started sessions through, so you still have to inspect for the session ID if it's well known, and for the for the other sessions, so you don't start new sessions. Or there are other strategies around. So in some places, it might be better to start fresh work than taking care of the stale work and stuff like that. There's dozens of strategies, depends on your situation. And how can you retrieve that load? I mean, there are also lots of situations or lots of alternatives. For instance, you can use some JMX access for your server. You can have, usually most of the monitors have some APIs around. You have the SNMP traps you can also register on, and it's not too hard to get that stuff in place. Only thing you should take care about is that you're not going to try to access the load with every single request, because usually it's a call to a remote system and it would slow down your system terribly. So it's better to have a different thread polling once in a while the load and having it in a shared state available on your machine, so read only, so that your filter is just reading a cached value. You can use Hazelcast, you can use anything else to share stuff across threads and machines and processes. That's quite straightforward. Also, not a lot of magic, a few lines of code and a few minutes of thinking up front. That should work. Tuning the load shatters, yeah, make it configurable, adopt it to historic patterns and all that stuff. I mean, quite straightforward. And you have alternative strategies, so you don't need necessarily to shed the stuff. There are also other patterns around, like you can, for instance, you can share load, which means that if you figure out that your system goes under load, you fire up another server, and you can combine these strategies. A lot of things to do to refine that pattern. But in the beginning, if you start with that, again, your system is a lot better than it was before, when you were not using that pattern. So let's look at the clock. It's not so much time, so I will show you this one pattern and we will skip the third case study. I will just tell you a few more things about that later. So one more pattern I just want to sketch is this deferrable work, which says, yes, I've got my requests here which hit my resources, but it's not the only producer of load. I also have some routine work going on, which is going to hit the load on those resources. It could be some maintenance job going on, some batch job going on in the background processing. It could be some map reduce, whatever. And the problem what you have is, if you look at here, your load of the machine, and if you get across the 100%, you get into a load, into an overload area, which gives you decreased responsiveness, sorry. And if you don't implement that pattern, so if you just have a little bit of standard request processing and this overhead of routine work, everything's fine. It's still fine, but if you don't implement the pattern, if you get more of request processing, you run into an overload area. And actually, it's not what you want to have. What you want to have is a pattern like that. You just want to defer this routine work because your request processing is more important in this place. To implement that, what I did here, also again, something very simple. I just emulated a batch processing loop by a few lines of code. In reality, it's a little bit more complicated, but it's the batch processing part and not the pattern part. So I just say my batch processing is I initialize some kind of state, and while the state's not done, I process the next step, filling in the state, and it returns the state again. So it's quite similar to what most batch frameworks do in some way, but it looks a lot more complicated if you go look into Java batch or into Spring Batch or in some other frameworks which provide you with that stuff. But basically it's moving through a series of state and doing a lot of work in between. And again, we try to retrieve the load, and if it's higher than it was quite a fixed threshold that we provided, we just wait for some time, and then we try again, and we wait and we wait. So only problem here, it's terribly easy to implement, and it helps you a lot with that situation. The only problem here is that your batch might starve in between. What you can do here is then just change the strategy a little bit, and you wait load-based, and you make sure that every time at least one step is going to be processed, but then depending on the load you have, you calculate a different delay and wait for a certain time. So you wait longer. The longer, the more load you have, the longer you wait. But again, you can adopt that. You can implement smarter strategies. It's just how to put that into your code. Here, the idea. It's quite straightforward. You can tune all that stuff again. And here, maybe you can even afford to retrieve the load every single time because usually you don't need to reach this loop. Usually takes a lot of processing steps before the next step is going to be evaluated. So maybe you can do that a little bit easier than in the other situation. Yeah. So that's basically what I wanted to talk about. Just give you a few ideas about further reading. So skip the third case study here. I think it's better to talk in depth about 2 case studies than just hurrying through 3 of them. At least that's my experience, therefore I decided to go that way. Some more reading if you want to learn more about that. As I said before, Release It. If I would have to decide, it would be a must read for every single developer. The Release It from Michael Nygaard. It's a great book. So have a look into that. Try to get a grip on that. It's a real great book about building systems for production, resilient system. Hanma also write a quite cool book about fault tolerance patterns. It's a book of this pattern series, Patterns of Software Architecture series. It's volume 3 or 4, something like that. Then there's a nice paper which you can download on the internet, which gets a lot of scalability and fault tolerance patterns from James Hamilton. He was a chief architect with Windows Live system when building that stuff, so Scalable's cloud service. And of course, the classic one, Distributed Systems from Andrew Tannenbaum. I'm always surprised. I have this book for 10 years meanwhile, and whenever I get into a new topic of distributed systems, I say, I'm curious if there's anything about that stuff in the Tannenbaum book. And I think this time there will be nothing. And I'm always wrong. It's unbelievable. I've got the impression that this book rewrites itself while standing in the bookshelf, because every time I look into it, I find something about the stuff I'm just curious about. It's a great book, actually. And if you just slept through the last 45 minutes, this is the sentence to keep in mind from this talk. It's all about production. We write our system for production and for nothing else. And for fun, of course. Okay. But on the other hand, writing resilient systems is fun. It's work, but it's work that really is fun to do. So I can encourage all of you, try to get a little bit more resilient and change the software world with that. That's what I had to talk about. That's what I had for these 45 minutes. Thanks for your patience. Thanks for listening.